So guys, welcome back. Today we start talking about 4.7 clustering by spectral methods and K-means. So this is the outline of the presentation. I'll talk about the clusters and mainly about the four methods we will expose in this presentation and the next one. The Fiedler Vector, the Modularity Matrix, Minimized Normalized Cut, and K-means. So first of all, as an introduction, in fact, the main purpose is to understand what a graph with many nodes and not all possible edges. And an important starting point, in fact, is to separate the nodes into what we call clusters, like groups of friends. And edges are more likely within the clusters than between different clusters in that case. So what we hope for is that the clusters have similar size, so we are not just picking off a few loners. And as an application for that, for example, clustering has been used in identifying these clusters will give a first rough understanding of graph, of course, but clusters have been identifying and decoding genetic data to cluster genes that show high correlations or anti-correlations. And cluster genes may lie in the same server path. So as an example, the following figure shows that we have 5 nodes, and in fact, those nodes have been separated into clusters. The points marked by star, in fact, are called the centroids. They're not exactly nodes or vertices of the graph, but these are the centroids of what? Of the 2 clusters. And these are their coordinates. 2, 1, and -1, 2, 3, and here we'll show how they have been obtained. So the first centroid, as you see in this graph, where we have 5 nodes, the 3 nodes that we have here, -3, 0, 0, 0, and 0, 2, are connected. So they are adjacent to each other. While the 2 remaining nodes, 1, 1, and 3, 1, are connected to each other. Okay? In fact, this is not a connex graph. You see, there is no link between the 2 clusters. Okay, that's why you have a dashed arc. So the centroid, in fact, what does it represent? It represents the first centroid represents the average, which is between half 1, 1 and half 3, 1. So it is at the center of the first cluster, the small one of the 2 parts. And the second centroid is also the average of the second cluster. So since you have 3 nodes in this second cluster, which is the triangle, you will take just 1/3 multiplied by 0, 0, 1, 3, 0, 0, 0, 2. So we get these 2 centroids. In fact, what happens with these centroids, C1 and C2, in fact, they do minimize the sum of the squared distances from the centroid to each one of the points in the cluster. Okay. Keep this in mind. I'll come back to it right now. In fact, these clusters were produced by the famous K-means algorithm with K equals 2. Well, this is a simple way to cluster the nodes, but not the only way. In fact, one way to deal with it when we have large matrices. So the way we've dealt with it using these averages to define the centroids is not quite efficient, and it's not practical when we have very large graphs. So what we can do then is to use what we call a CR factorization and approximate our matrix A, the agency matrix, by a CR factorization. The CR, of course, you're going to obtain is low because C has only K columns and R has K rows. And in the K-means approximation, the columns of C are the centroids of the clusters, and each column of R has a single 1 and K-1 zeros. So they'll be just defined by zeros and 1, which is a perfect, in fact, encryption of the information. More exactly, at every entry ij, Rij is equal to 1 or 0. If the centroid I is closest or not to the point xj. And the ones in the row I of R tell us the cluster of nodes around the centroid marked by star in the column I of C. So for the 5 nodes and 2 star clusters we had in the previous graphs, R has only 2 different columns. So let's go back to that previous slide. So this is, guys, what is it here? These are the coordinates of the 5 points that you have here, right? You see 0, 0, 1, 1, 3, 1, what else? 0, 2, and negative 3, 0. Right? In fact, what was done here is an approximation of this of these points. So first of all, let us just interpret the approximation. What does the -1, 2/3 represent?
The centroid.
The centroid of the cluster to which belongs the point 0, 0, right?
Yes.
So basically, you have just in this approximation, you have just 2 different terms. -1, 2/3, -1/2, 2/3, -1, 2/3, to represent the centroid of the cluster. So each point is substituted by the coordinates of its belonging or its cluster's centroid. Now, what about 1, 1, 3, 1? They were substituted by the centroids of their corresponding cluster. Okay? And this now could be written simply as -1, 2/3, 2, 1 multiplied by 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0. So here you see that the columns, the columns of R, how they have been obtained. It just encrypts the fact that that point, in fact, 0, 0, in fact, belongs to the cluster with centroid -1, 2/3. And the next one is telling you that that point 1, 1 belongs to the cluster with centroid 2, 1. Got it? Okay. So it's just this was obtained by the K-means algorithm. In fact, to do things formally, let's say that the way the previous example was handled is probably not the fastest or the best way for a large set of nodes. And in fact, many algorithms have been and will be invented to partition a graph. You can always tune something to get a way to cluster things. So we focus, in fact, on 4 successful methods that extend to more different problems. Mainly, I will talk about spectral clustering using what we call the Laplacian of the graph and the modularity matrix. We'll talk about minimum cut, and we talk about weighted k-means. So first of all, let's talk about the Fiedler vector. So what is the purpose of the Fiedler vector? Is to find the vector z that solves the following equation, where ATCA z is equal to lambda dz. Now this guy, ATCA, is the graph Laplacian. Okay? And its diagonal d contains, as we said, the diagonal of the Laplacian is what? Contains the total weights on the edge, or the degrees on each for each node. So in fact, D normalizes the Laplacian, and the Fiedler vector has the vector 1, 1, 1 for the first eigenvalue equal to 0. And the Fiedler eigenvalue is the next one, is lambda 2. And positive and negative components of its eigenvector indicate the 2 clusters of the nodes, if you apply. Now the next part is to talk about modularity matrix, where the Laplacian ATCA is replaced by the modularity matrix M. And here we have to choose the eigenvector that comes with the largest eigenvalue. Again, it will be positive and negative components that it will be the positive and negative components that indicate the 2 clusters. So M is in fact the agency matrix just talked about, -1/2m multiplied by d dt. What is d? D, small d, gives the degree of n of the n nodes. I mean the number of edges adjacent to the n nodes, as we just talked about. So each row and column of M is what? Is equal to MT. So M is equal to MT, which means that M is symmetric. And as to 0, so one eigenvector of M is again 1, 1, 1. If its eigenvalue lambda equal to 0 happens to be the largest, so M has no positive eigenvalues. So if the largest one is equal to 0, all remaining eigenvalues are less than 0, then all nodes will be and should go into the cluster. And this way we uncover the clusters. Okay. The next way to deal with this is what we call the the minimum normalized cut. And the idea is really smart. We would like to find the minimum normalized cut that separates the nodes into clusters P and Q. Okay? So the unnormalized measure, in fact, before normalization of a cut is the sum of edge weights, or what we call Wij, across that cut. In fact, those edges connect a node in cluster P to a node outside of P. Okay? Because sometimes nodes corresponding to two different classes might be connected, although you belong to a different cluster. So weight across the cut should be minimized. And how to get this? You sum up the weights on the links that connect the two clusters. So if you take the links in P, you sum up all the weights that connect two different nodes where I belongs to P and J doesn't belong to the cluster. So by this measure, in fact, a minimum cut could have no nodes in P. So we have to correct this. So what we do a normalization. We normalize by the sizes of P and Q. And these are the sums of the weights inside the clusters. So the size of the cluster is given by the sum of the weights of the edges in the cluster for Ij in P. Okay, I and J in P. Okay. Note that an edge inside P is counted twice because you will count it for Ij and Jr. So you're doubling the weight, in fact. So what you get are the following measures. So this is the normalized, what we call the normalized K-Cut. The unweighted size would just count the nodes and lead to the ratio cut. Here we divide weight across the cut by the weighted sizes of P and Q to normalize the key quantity N cut. So what we obtain in bold here is a normalized cut weight we call N cut of P and Q, which is the sum of the links in P divided by the size of P, plus the sum of the links in Q divided by the size of P. Okay, so the definition of the N cut, in fact, extends from two clusters P and Q to K clusters, P1 till K, and this way you can define what we call the normalized K-Cut, where N cut of the clusters P1 till Pk is the sum from I equals 1 to K of these links of Pi divided by the size of P. So let me go back to this. So we said that the size of P is the sum of the weights of the arcs in P, and each arc Ij, of course, is counted twice. Okay, which means here, so for example, in a graph, guys, let's say this is a simple cluster. I have these three nodes in a cluster P, but although they are connected, these connections may have different weights. So let's say these are the weights. These are the Wij's. Okay, got it? So what is the size of P here? So this is P to me. This is the first cluster, P. What is the size of P? Are you with me, guys? So what about the connection between 1 and 2? I'll have 4 plus 4, right? Because I count 1, 2, and 2, 1. Plus 5 plus 5. plus 2 plus 2. Okay? So this is the size of this particular cluster, which is 8 plus 10 plus 4, which is 22. So let us assume that there is another cluster here. Let's call it Q. Okay? And I have it just composed of 2 nodes. So I call them 1, 2, 3. I'll call them 4 and 5. Okay? So this is 4 and this is 5. And the weight here is how much? The weight, let's call it, let's say it's 3. Okay? Now, what is the size of Q? Size of Q is just this weight multiplied by 2. So it's just 6. Okay? Got it? So here we were able to compute the lengths. Now, for this length between 3 and 4, let's assume it has a weight of 1. Okay? And I may probably give another length here just for fun. Perhaps a length like this. Okay? So, in fact, the weight across the cut, if I'm cutting like this, what is the total weight across the cut, guys? Across the cut that separated the 2 clusters, P and Q, the sum of the weights is 1 plus 4. It's the sum of the weights on the 2 vertices from 3 to 4 and from 1 to 4. It's 1 plus 4, which is 5. Okay? Got it? So that's it. This is the last slide I had for you today. Hopefully, we'll continue this next time.